In this video, I'm going to go through some basic notes about gravity. Now, I know you might be already thinking, don't we already know about gravity? Isn't it Fg equals mg? And the answer to that is yes, sort of. So we already know the equation or the idea that the force of gravity acting on the object is the mass of the object times the acceleration due to gravity, or the gravitational field strength. So this equation is great if you know g, but what happens if you don't know g? Well, that's when we have to use this other force of gravity equation, which usually occurs for when you are off the surface of the Earth, or you are on some distant planet or asteroid or thing like that. So the equation for the actual force of gravity is g m1 m2 over r squared. So really I should write this as g, the mass of the object, times the mass of the planet, okay, or asteroid or whatever else we happen to be on, over the distance from centers. And I'll explain more about that in a second. So don't think of r as radius, think about it as distance from centers. So big G is a gravitational constant. So again, gravitational constant. Okay, very different from little g, acceleration due to gravity. Gravitational constant has a value of 6.67 times 10 to the negative 11 Newton meters squared over kilograms squared. And this is on your reference tables, so don't feel like you have to memorize it. That being said, you do have to plug it into the equation every single time. Okay? Like I said before, r is not radius. We might use the radius, but r is really the distance from the centers. Okay, so if I have, let's say, two planets, X and Y, actually make them slightly different shaped, Y, okay, the distance, or the R, that I would need to plug in into the equation is not the radius of planet X or the radius of planet Y. Instead, it's the distance between their two centers. Okay, so where that really comes into play is, let's say we have Earth and we have some satellite floating above Earth. Okay, so our distance from centers is something like this, r, okay, or a distance from centers. So that r represents what's usually called the altitude, or the height above the surface, plus the radius of the Earth. The radius of the Earth is usually given to you if you need it, but just remember that this r value here would really be the altitude plus the radius of the Earth. So that's something we have to keep in mind. Okay, so let's talk about how the AP exam really likes to use this equation, because substituting in actual numbers to this equation is kind of annoying. So the way that AP loves to use the equation is they'll say, okay, you have some planet M and some satellite above planet M at a distance r. And they might ask, how does the force of gravity in orbit compare to the force of gravity on the surface? Okay, so on the surface, the satellite is a distance of a radius from the center of the planet. Okay, let's say its altitude is exactly equal to the radius of the planet. Okay, so we are now at a grand total of 2 radii of the planet from the center. Okay? So the masses haven't changed. Big G hasn't changed. What has changed is we have doubled the distance. So we essentially want to ask ourselves, if we double that R, then what happens to FG? Okay. So this is where we might use that whole base case idea. So remember, base case idea says start with the equation and then say everything initially gets a value of 1. I'm going to keep G in terms of G. So mass 1 is 1, mass 2 is 1, and the R is 1. So that means my force of gravity is just based on G. Then do what the question tells you to do. So in this case, we need to double R. So instead of 1, I'm going to have a 2. Well, that gives me 1/4 G. So what this means is that FG has changed by a factor of 1/4. So if I double the distance, then that gives me 1/4 FG. Okay, you can do the same thing with masses. So if we double the mass of the planet, but then keep everything the same, okay, then what FG? Well, originally, everything gets a value of 1. So that gives me 1G. Then, if I double one of the masses, just 1, that gives me 2G. So there's a factor of 2 change here, so that means I have doubled FG. Okay. Or I could say something like, well, what happens if I half R? Then what happens to FG? Okay. Again, everything initially gets a value of 1, just to make life easier. I'm not saying the mass of a planet is 1 kilograms. That's impossible. So if I 1/2, 1 over 1/2 squared, that gives me a G over 1/4, okay, which is actually the same as 4G. So again, this is a change of a factor of 4. So if I half the radius, then I quadruple FG. Okay. R and FG have a really cool relationship. If I was to graph it, it would look something like this. And we say that they follow the inverse square law. Okay. Because R is on the bottom and it's squared. Inverse meaning on the bottom, square meaning squared. Okay. So that's about it for the new force of gravity equation. Okay. Now let's talk about Newton's third law and this idea of gravity. So here is our planet Earth, and let's say here is the moon. Okay. We all agree that the moon has a force of gravity from the Earth. So I'm writing that as Fg on m. Okay. The Earth pulls on the moon, causing it to spin in a circular orbit. What we often forget, though, is that the moon also pulls on the Earth. Okay? Newton's third law says that in any interaction between two objects, the forces between those two objects must be equal in magnitude but opposite in direction. So what that means is the Earth and the moon interact through gravity. So the forces of gravity between those two objects need to be equal and opposite. So the force of gravity of the Earth on the moon has to be equal to the force of gravity of the moon on the Earth. Okay? The reason why the moon is the thing that does the orbiting is because the moon has a much smaller mass. Okay? So the moon has a much smaller mass compared to the Earth, which is very large. In order for their forces to be equal, the moon must have a very large acceleration compared to the Earth. It's the same sort of idea between the Earth and the sun. The reason why the Earth orbits around the sun is because the sun is so much more massive that its acceleration is essentially negligible. All right, so now let's talk about finding baby g. Like I said, we use this new force of gravity equation when we don't know either the acceleration due to gravity, oops, that's not g squared, or the gravitational field strength. So remember, g means acceleration due to gravity or gravitational field strength. They mean the same thing. They are the same thing. They are the same variable. You calculate them in the same way. It's just two different names. Okay. So the way we might find the acceleration due to gravity or the gravitational field strength is keeping in mind that the two force of gravity equations that we have are the same force of gravity. It's just one we use when we don't know g. So I can set these two equations equal to each other. Okay? And I'm going to replace the mass m1 and mass 2 with mass object, mass planet over r, keeping in mind that r is the distance, over g. Now, usually when we use this equation, this mass here is the mass of the object, and g is the acceleration due to the gravity or the gravitational field strength caused by the planet. Okay? So it looks like the mass of the object cancels. So I can find the gravitational field strength, or the acceleration due to gravity of a planet by doing g, the mass of the planet, and when I say planet, it could also be asteroid or some larger object, over the distance from the center. Remember, r is distance from center. Okay. So this might help me find the acceleration due to gravity in orbit. It might make me or allow me to find the gravitational field strength on Mars, any sort of thing like that. Okay. Now this equation is not on the reference table, so it is one that I recommend that you memorize. And it'll make your life a lot easier. Okay. So now let's talk about gravity moving things. Okay, so gravity causes things to move in circles. So what does that really mean? Well, let's think back to circular motion, right? If gravity causes things to move in a circle, then Fg is our centripetal force and is our mass times acceleration. Okay, well, what is the acceleration of something moving because of gravity? Well, it's just g, the gravitational field strength, or the acceleration due to gravity. So I can set g, if I know it, equal to v squared over r. I can set Fg equal to mv squared over r. Okay. Now you might be thinking, oh gosh, this seems complicated. It's really not, because oftentimes a lot of things cancel for us. So when we're using this equation, usually the Fg we use is the bigger Fg equation, meaning the g, mass object, mass planet, over distance from center is mass. Remember, this mass is the thing doing the moving, so it's the object, because the planet's not going to move. V squared over r. So mass of the object cancels out. One of the r's cancel. Okay, so we're really left with g, mass of the planet, over r, is v squared. So we could actually solve for the orbital velocity by just taking the square root of both sides, where r is the distance from center. So this is actually what NASA engineers do. They figure out where they want their satellite to be using r, and that allows them to figure out how fast the satellite needs to be moving in orbit so that it has a stationary orbit. Okay? Now remember, satellites orbit the Earth in nice circular patterns at constant velocity. So once we find that orbital velocity, it is a constant velocity. The constant velocity for anything moving in a circle is 2 pi r over the period. Okay, I know sometimes we use capital T for tension. It's also period. If it makes more sense to you to do a lowercase t, that's totally fine. Okay, so we could set this orbital velocity equal to 2 pi r, again, where r is the distance from center, not a radius. Distance from center over the period. That might allow us to find the period of revolution of the satellite, meaning how long it takes to actually travel around the Earth. We might know the period of the satellite. For instance, there are things called geosynchronous, I think that's how you spell it, satellites, which have a period of 24 hours. They actually stay right up on top of one single point on the Earth, so you don't actually have to move the receiver antenna. It just points at one single satellite. Okay. So this is a very useful equation. Again, it's just not really anything new, just remembering that gravity can be a centripetal force, does cause things to move in circles, and kind of all the consequential equations from them. Okay. So we already talked about that, orbital motion. Okay. Last thing I want to talk about is a new potential energy. So our old potential energy is the idea that PEG is mgh, okay? Which is great if we know the gravitational field strength, which we do not always know. So PE, I like to call it PE big G. If we don't know the gravitational field strength, the new potential energy is big G, the mass of the object, times the mass of the planet over the distance from the center. No squared, no nothing. And on the reference table, there's actually a negative from that. And that has to do with the fact that the work done moving the planet is negative. Okay? So really what that means for us is more negative is less than less negative. So like negative 20 for once is actually less than negative 10. Okay? So oftentimes questions will be asked about the potential energy as compared to the distance. Okay? So as this distance increases, PEG is going to decrease, but it's negative. So it's really going to look like something like that. Okay? So as R increases, PEG decreases. So the farther away you are from a planet, the less potential energy, the more potential energy you have. So where we really like to use this on occasion is to figure out escape velocity, meaning how fast you actually have to move to escape the gravitational pull of Earth. Okay, so very similar, we can set PEG instead of equal to KE. So sort of same type of conservation of energy treatment that we might do on the surface, but this time for an object out in orbit. So we have G, mass of object, mass planet, over R. It's the object that's actually doing the moving, so that cancels, and we could solve for V if we wanted to. The 2 moves over, and planet over R, and then we take the square root. And that gives us our escape velocity. Okay? Don't confuse this with orbital velocity. It is rare that you need to use this equation, whereas orbital velocity, way more useful. Okay? So let's talk about some planetary motion and conservation of energy. You probably did a lot of this in earth science already. So let's say we have the sun here, because we know our planets move in ellipses. We have the Earth over here, and then we have the Earth over here. Now, a lot of people know that the Earth moves faster when we are closer to the sun and slower when we are away from the sun. Okay? The reason why is because the farther we are from the sun, the smaller gravitational potential energy we have, right? Because if we increase that R, then we are decreasing PEG. Whereas when we are closer to the sun, okay, we have less PEG. Okay? Energy has to be conserved. Wait, nope, I messed that up. We have more PEG. Why? We have more PEG here. because again, it's less negative than when we're closer, right? Going back to this graph, the farther we are from an object, this is more PEG, this is less PEG because we're on the negative side of the axis. Okay. So we have more PEG the farther we get away from the object, which means we have less kinetic energy. Okay. And then when we get closer to the sun, we have less PEG, so we need to have more kinetic energy because energy is conserved. Okay. This idea of planetary motion and gravitational potential energy at a distance is a lot more rare than the rest of the stuff with gravity that I talked about. So most important things that you guys need to be aware of is this Fg m1 m2 over r squared equation, and the idea that gravity can be the centripetal force, which we can then set equal to MAC, and all of the different consequences from that. And also the idea that the two FGs are the exact same FG, and from that we can get that the acceleration due to gravity, or the gravitational field strength, is g times the mass of the planet over the distance from center squared. Okay. Again, these are the two major takeaways. The potential energy stuff more so in his side. Okay. But also most commonly asked in this planetary motion type problem. And that is it for gravity.